Question 7. The diagram shows the curve y equals root 3 over 4x plus 1 between 0 and 20. So that's this diagram here. The point P on the curve has coordinates 20 and 1/9 of root 3. The shaded region is enclosed by the curve and the lines x equals 0 and y equals 1/9 root 3. Find the exact area of R. So, to find an area under a curve, we're going to use integration, but we have to be careful with our final answer that we exclude this little rectangle that's underneath the curve there. Okay, so I'm just going to get rid of that picture so that I've got space to do my working out. And we're going to start off by integrating root 3 over 4x plus 1. And we're going to do it between 20 and 0. So, root 3 over 4x plus 1. I'm going to turn this into a form which is more suitable for integration. Let's try and get that focused a bit. So still between 20 and 0. I'm going to separate this square root using surd rules into this. And then, because this is a constant, I'm going to bring this outside of the integration. And I'm also going to rewrite this as a negative index. So it's going to be 4x plus 1 to the minus 1/2. It's in a format we can integrate now. So we're going to integrate this using a technique called integration by inspection. So I'm going to put my root 3 there and my square brackets ready for my answer. So I know that when I integrate this, I'm going to get some function involving 4x plus 1. I also know that this power will increase by 1, so that's a half. Now, working backwards, I think what would happen if I differentiate this function? Well, I would end up multiplying by 4, and I would end up multiplying by a half, and 4 times a half is 2. So I would end up, if I differentiated this, with a 2 out the front of here, but we don't have a 2, so we have to correct for that by putting a half here. If we differentiate this now, half times 4 times a half, we get 1, which is what we would have here. This is between 20 and 0. So I'm going to bring this half outside my bracket again. So I've got root 3 over 2. Substituting in the limits now, I'm going to have 4 times 20 plus 1 to the half, which is just a square root, minus, well, when I put 0 in here, I end up with 1 to the power half. Now I could put all this into my calculation in one go if I wanted and get out an answer, but I'm just going to simplify it a little bit before I do that, because here we've got 81 to the power of a half, and now we can see that. We know that's going to be 9 later on. Anything, well, 1 to the power of a half is going to be 1, so we've got to take away 1. And if we do that, we get 4 root 3. Okay, remember that is not our final answer, because if we just go back to the curve, we've got to take away this bit that's underneath the rectangle. Oh, sorry, underneath the this rectangle is underneath the curve here. So let's have a think about the dimensions of this rectangle. Well, we know the point P is 20 and 9th root 3, and we've got even got the equation of the line y equals 1/9 root 3. So this point here is a 9th root 3, and this point is 20. So the area of the rectangle equals 20 multiplied by 1/9 root 3, which I'll write a little bit more simply as 20 over 9 root 3. So the region R is going to be our 4 root 3 minus 20 over 9 root 3. Pop that into your calculator or manipulate it another way, you get 16 over 9 root 3. There's our answer to part A. Question 7, part 2. Find the exact volume of the solid obtained when R is rotated completely around the x-axis. So, when we rotate this curve around the axis, we're going to have another little bit missing here, a little bit like the last question, but instead of it being a rectangle underneath the curve, it's actually going to be a cylinder. If you think about rotating a line around an axis, it's a cylinder out of the 3D shape that this curve will make. Okay, so we're going to, very similar to last time, we're going to use volumes of revolution to find the volume of the whole shape under the curve and then correct for this cylinder at the end. So we'll get rid of the diagram. If I want to find the volume when I rotate any curve around the x-axis, I use the formula pi, the integral between my limits, so point P and 0 of y squared dx. Now don't worry that we've got a y here and an x here, because we're going to substitute in our curve for y here. So we get pi between 20 and 0, and our function is square root 3 over 4x plus 1 squared. Now that's nice because this square root and that squared are going to cancel out, giving us a simpler function. So between 20 and 0 of 3 over 4x plus 1. So to integrate this, well, I know if I integrate 1 over x, I get log x. So I know when I integrate this part here, let me just put my pi there, I'm going to get some function involving log of mod 4x plus 1. Okay, that's not the whole story though, because if I differentiated this, I would get a factor of 4 at the beginning, and I've also got this 3 here. So instead of having a 4 and this 3, I'm going to get 3/4 out of here. Now if I imagine differentiating this whole function, well, this 4 will cancel out with this 4, and I'll just be left with 3 here, which is what I've got here, because I want this to differentiate to that. So that's my integrand. Between 20 and 0, let's substitute in the limits. We're going to get, well, let's bring the 3/4 pi out here as well, so we don't have to deal with that twice. We'd get log, well, 4 times 20 plus 1, we did that before, that's log 81, minus log, well, when that's 0, log 1. This simplifies nicely because log 1 is 0, so we get 3/4 pi times log 81. Okay, don't put that into your calculator because up here it says find the exact volume of the solid, so we don't want any decimals in our answer really. We want to leave it as a fraction, and we want to leave the pi and log in the answer. So now we're going to take account, let's just go back for a second, of this little bit underneath the curve. Now there's two ways you can do that. I'll do both. You wouldn't have to do both in your exam. The first one I'm going to do is just do the volume of revolution for this line. So imagine I'm rotating that line. Forget about the curve. So that would mean, we know the equation of the line is y equals 1/9 root 3. So the volume created by rotating that line around the x-axis will be pi integral between 20 and 0 of 1/9 root 3 dx. Oh, sorry, that's squared. Okay, so let's simplify that before we do it. We get 20 and 0, 1 over 27 dx. So we're just integrating a constant here. Okay, so if I can even bring that outside the integral if I wanted before I started. If I do that anyway, I get pi over 27 x 20 and 0. You could still have x over 27 in here if you wanted. So when I put 20 into that, I'll get 20 pi over 27. When I put 0 in, that will cancel and go to 0. So my answer is 20 pi over 27. Another way I could have done this, I could have imagined, well, this shape that goes around the x-axis will create me a cylinder. And I know the radius of that cylinder is 1/9 root 3, and I know the length of it is 20. If you can remember the formula for the volume of a cylinder, you're going to do pi r squared times the length. And if you simplify that, you get 20 pi over 27. So the same answer either way. It doesn't matter which way you do that, you only need to do one of them. Still not quite finished yet though, because we need to say, well, R is going to be the volume created by the curve minus the volume of our cylinder underneath, which gives me, if I just bring out a common factor of pi there, 3/4 log 81 minus 20 over 27. Okay, remember we want an exact value for the answer here.